Well, hello everyone, and welcome to Lecture 5 on the SE4014 Material Science and Engineering course. So today I would like to talk about stress and strain. I'd like to come up with some definitions for stress and strain and ask why they are used instead of considering the load upon a material and its deformation. I would like to define what we mean by the elastic behavior or the elastic region of a material, and consider what happens when the load placed upon a material is quite small, and consider how much deformation occurs under such circumstances. And then to move on and consider the plastic behavior or the plastic region of a material, and discuss at what point deformation occurs. We'll have a talk also about toughness and ductility. We'll define them and consider how we measure them, and discuss the hardness of a material. So imagine that we take a material, and for the purpose of this course we'll assume that we're dealing with a metal, and we subject it to a small load. We could place it under tension. We could pull the material apart and place it under a small load. Now that material will experience some kind of displacement. It will, in the case of a simple tension experiment, it will elongate. The material will get longer. Remember that we're only applying a small load here. Because we've only applied a small load and the material displacement is minimum, when we remove that load, the material returns to its original shape. It resumes its original form. And this is really the very definition of elastic deformation. It's deformation that isn't permanent, i.e. when we remove the load that we've applied, the material returns to its original form. It only applies for most materials for relatively small loads. And if we think about this on the atomic scale, we're only talking about bonds stretching slightly. So we're not placing bonds under such pressure that they rupture or they break. We're talking about a very small load that causes only small stretches in bonds and only very, very minor perturbations in atomic position. Importantly then, as we said, those bonds that make up the crystalline material of the metal return to their original configuration the moment that the load is removed. And importantly, if you were to plot the load or the force that you apply to that material versus its displacement, then that region is linear. There is a linear dependence. Importantly then, elastic deformation is entirely reversible. Now, if you compare that to the plastic deformation of a material, we're now talking about some kind of deformation that is permanent, that cannot be reversed. So we place a material under a slightly larger load now, and we enter this plastic deformation region, and the material once again is displaced to some degree, dependent on the load that we place upon the material in question. And upon the removing of that load, or the removal of that load, we still have some kind of deformation, some kind of displacement. Now, there will be both an elastic and a plastic component to that. And importantly, the displacement that resides after the removal of the load is entirely plastic in nature. Importantly then, we're now talking about some kind of deformation that is permanent. Those bonds stretch and start to break, and we're unable to recover the initial state of the material. And planes also shear, so atomic planes start to shear Okay, they start to break essentially. And importantly then, if we compare that graph where we're plotting the force versus the displacement, if you like, of the material, we now enter a non-linear regime. Okay, so the dependence of force versus the displacement of the material is no longer linear. Now, as we said at the very start, when we looked at the learning objectives, when we get this data, we'll talk about how you measure the, for example, tensile stress of a material, or how you measure the fracture point of a material under some kind of load. But the data that you gain from an instrument and the data that you're going to see in your coursework is raw data as a force applied, so the force that you've applied to a material versus the displacement of that material. Okay, essentially how much it's been elongated. Now that's the raw data, and it raises the question as to whether or not that data is in the most useful form. Does that tell us everything we need to know about the material? And of course it doesn't. We have to process that data to some degree. If you apply a very small tensile load to a material with a very high cross-sectional area, that tensile load will have very little impact. However, if you were to apply that exact same load to a material with a very low cross-sectional area, then you might expect a high degree of plastic deformation. So we need to do something to the data in order to normalize it for the cross-sectional area of the material, to take account for the cross-sectional area of the material and tease out, as it were, the material properties that are independent of cross-sectional area. Because of course we don't want to look at data which is dependent on cross-sectional area. We want to obtain information about a material in its purest form. We don't want it to be specific to the sample that we're measuring at the time, or the size or the dimensions of the sample we're measuring at the time. And we achieve that effect for normalizing for the cross-sectional area of the material by considering the engineering stress that we apply. So here we take the tensile stress that we apply. Let's imagine we're taking a tensile stress measurement where we're pulling a material apart, and we divide that by the cross-sectional area of the material before any load has been applied, because of course if we apply a load then we're likely to change the cross-sectional area of the material. Importantly then, this is the force that's required to deform the material, and it is independent of the cross-sectional area of the material. So on the previous slide I showed you 5 or 6 rods of copper that had differing cross-sectional areas. Now if we took a tensile stress measurement and we were trying to work out the load that was required to deform those materials, we would expect a different result for every single copper rod on the previous slide. If I were to divide these measurements by the cross-sectional area of the material, then we would gain a consistent result for each rod, independent of its cross-sectional area. The units of engineering stress then are, you'll see them in the textbooks, written in various different ways. You can have pounds per square inch. Of course, that's not really what we like to use as scientists and engineers, so we tend to use newtons per meter squared. You also see newtons per meter squared written as pascals, where 1 pascal is 1 newton per meter squared. So be careful with units. You'll quite often see this written as pascals. Now you can also get shear stress, And this slide really here is to highlight the fact that we can apply stress in more than one way. We don't just have to yank a material apart under a tensile load. We can also measure different stress states. So here is the shear stress. Again, you'll note that we are dividing the applied load by the cross-sectional area of the material. And in any device, and this is important for all applications in physics and engineering, any device is experiencing a number of different stress states. So look at this fairly rudimentary piece of equipment here. It's a ski lift. The cable is under simple tension. It's being pulled in two directions. And the drive shaft is under a shear stress. It's turning under and is experiencing a shear stress. Things can also experience compressive stress or compression. So this, if you like, is the opposite to placing a sample under tension, where we're yanking it apart, we're pushing it together. And you can see there's a good example of the rock there. Bridges experience compression under the main section of the bridge there. But there are also other forms of stress. If you think about a pressurized tank, that's experiencing something called biaxial tension. It has a gas under pressure that is pushing out on the walls of the tank. And indeed, a fish underwater is experiencing hydrostatic compression. It's having to deal with its skeletal structure, is having to deal with the pressure of the aquatic environment that surrounds it. And of course, here we're not really thinking about area, we're more thinking about volume. So we would normalize the stress there to the volume of gas or the volume of the fish's body. Now, this is interesting from an engineering aspect because often we have to think about the design of vessels that can transport various things that are able to withstand very high pressures. You think about, there are a number of examples. You think about an aircraft that has to operate in low pressure, but has to be pressurized in order to keep the inhabitants of the aircraft safe. The walls of that aircraft have to be able to withstand the pressure there. And I think possibly one of the most interesting examples is a submarine. So we have a class of Vanguard submarines that carry our Trident ballistic missiles. They are our nuclear deterrent. One of those submarines is HMS Vengeance, and it's able to dive to depths in excess of 250 meters. Although if you look on the Ministry of Defence website, the actual service depth is classified. But if you just calculate the pressure that submarine has to withstand at a depth of 250 meters, it's about 25 atmospheres. It's 25 times the pressure that we experience at ambient pressures, in the room you're in right now. And of course, that places the vessel under a considerable amount of hydrostatic compressive stress. That's before, right? So that submarine has to experience those kinds of pressures. The materials that it's made up from have to be able to withstand those kinds of pressures. And that's before you take into account any potential attack from an enemy. And indeed, these things are able to withstand, again, you can't really find the exact numbers for this because it's classified information, but they are able to withstand some potential attacks in the form of usually explosives and torpedoes and that kind of thing. Now, if we've got engineering stress, then we must have engineering strain. And strain is what happens to a material in the presence of stress. It is a dimensionless quantity, and it is the change in some kind of size parameter of the material. So you can see in the case of an applied tensile stress, where we are pulling a material apart, we would use the term tensile strain. And it is a measure of the total amount that a material stretches relative to its original length. So it's the change in the length of the material divided by its initial length. Now, if we place a sample under some kind of tensile stress or strain, it will get longer. We're pulling it apart, so it will get longer. The sample becomes thinner in the plane that's perpendicular, and that lateral strain will have a negative sign to show you a change in size. The sample will become thinner in the plane that is perpendicular to the applied tensile strain, right? If we're pulling a material apart, it becomes thinner, it becomes longer in the direction that's in the direction of tensile strain, but it becomes thinner as we pull it apart. The direction of its thinning, if you like, is perpendicular to the applied load. So that lateral strain will actually have a negative sign because the material is becoming thinner. The strain in the direction that we're pulling it apart, which is denoted as L on the diagram there, will be positive because it's becoming longer. But the width of the material is decreasing as we pull it apart, it's becoming thinner. So that lateral strain actually has a negative sign. Again, we can also measure shear strain. And if we're measuring shear, then we're considering the angle of the material. So we can use the tangent of an angle to find the shear stress. One thing that I would like to note here is that I'm only ever going to ask you about tensile stress and tensile strain in coursework and the end of year coursework or exam. So an appreciation of shear strain is important, but I will only ever ask you about equations that involve tensile stress and tensile strain. Okay, so how do we measure these properties of a material? Well, we do so in a tensile testing machine, and this is important for your coursework. We essentially have a load cell that we can clamp the material into. So at either end of that load cell will be jaws that hold each end of the material. And there is a moving crosshead which is able to pull the material apart very slowly. And there will be some kind of extensometer, right? So that tells us how much we're pulling the material apart. Usually up to its fracture point. We're usually interested in measuring a material right up until a point it essentially breaks. So we clamp the specimen in and we pull it apart, and we can yield information about plastic region, elastic region, fracture point. We'll talk about some of these values in a moment. There is a standard way of doing this. So we would take a specimen that has quite specific geometries, and you find them usually in the form of, they're called dog bone samples. And you can see on the right there is a standard specimen for tensile testing, and it has, the shape of it is a dog bone essentially, and those wider regions at the top and bottom of the sample are where we would clamp the material in. The gauge length then is important because that defines the original length of the material. So that gauge length, not the ends of the dog bone, the gauge length is the part of the material that is experiencing the tensile load. So that forms our, when we're talking about calculating engineering stress and engineering strain, that forms the active area, if you like, of our sample. That's what we use to define the original length and the cross-sectional area of the material. Let's go back to that linear region, the elastic region of a material, and talk about some linear elastic properties. This is where Hooke's law applies, and I'm sure anybody who's done A-level physics, or probably even GCSE physics, will remember this equation. And during elastic deformation, a material is governed by Hooke's law. So engineering stress is equal to the Young's modulus of the material, or the modulus of elasticity, multiplied by the engineering strain. So engineering stress is our applied load divided by the cross-sectional area of the material. The Young's modulus you can think of as a measure of a resistance to a force. And the engineering strain is our initial length of the material, the length of the material under the applied load, so the stretch material, divided by the initial length of the material. Now, we can calculate the Young's modulus of a material by taking the gradient of a graph within the linear elastic region of engineering stress versus engineering strain. And indeed, these graphs are a measure, if you like, of the bond strengths of atoms within a metal sample. So we've got this slope of our stress-strain plot. That's proportional to this Young's modulus or elastic modulus. That's therefore normalized to the material properties of the sample, because remember that we've divided stress by the cross-sectional area and divided strain by the length. And it therefore gives us information about the atomic bond strengths of atoms within a metal. Now let's have a look at this example question. A cylindrical specimen of a titanium alloy has an elastic modulus of 107 gigapascals. It has an original diameter of 3.8 millimeters and experiences only elastic deformation when a tensile load of 2000 newtons is applied. Now that's important because only elastic deformation tells us that Hooke's law applies. And we're asked to compute the maximum length of the specimen before deformation if the maximum allowable elongation is 0.42 millimeters. So as I said, the first thing to realize about this particular problem is that it's a Hooke's law problem, because we're in the elastic deformation region of the material. We know that under this tensile load of 2000 newtons, only elastic deformation occurs. And what the question is asking us to do is calculate the length of the material at this maximum allowable elongation of 0.42 millimeters. So before we calculate that length, we've got to solve for strain. So we rearrange the equation to solve for strain, because remember, this is the part of the equation that is talking about length. So strain is equal to the engineering stress divided by the Young's modulus of the material. or the elastic modulus of the material, which of course we know is 107 gigapascals. And so we know E, the big E, we know the elastic modulus. We've got to calculate the engineering stress, which of course is the force applied or the load applied divided by the cross-sectional area of the material. Well, we know that the force applied is 2,000 newtons, so we just have to work out the cross-sectional area of the material, which of course we can do because we have a diameter and by inference we have a radius for the material. And when you do that, the engineering stress is equal to 1.76 times 10 to the 8 pascals. So we have a measure then for the engineering strain, small e. We've calculated sigma, or the engineering stress. The question has given us the elastic modulus, or the Young's modulus, and when you calculate that engineering strain, it's equal to 0.00165. So now we've solved for the engineering strain, we can work out the maximum length of the specimen, because we know that the engineering strain is equal to the length of the sample under the applied load divided by the original length of the sample. We know that the length of the material under the applied load is 0.42 millimeters. So we rearrange that equation to solve for the original length of the material, which is the length of the material under the applied load, 0.42 millimeters, divided by the engineering strain. And the answer you get there is 255 meters or 2.55 meters. Now, another parameter that you'll see for materials is something called the Poisson's ratio. If you elongate a material in one direction, then it will cause constrictions or strain in the lateral direction. And these are related to one another by a negative sign, i.e. if the material gets longer, then to compensate it must get narrower in X and Y. And it's very simply the ratio of the strain in those two competing directions. So we've spoken about tensile strain and lateral strain. This is just a measure of the ratio of those two. And it's a material property. So you can see there I've shown you that gold has a Poisson's ratio of 0.415, aluminium has a Poisson's ratio of 0.35. And you can also measure various other elastic properties that depend on the kind of stress that the material is experiencing. But as I said, I want you to focus on tensile stress and tensile strain for this module. So we've got another example question here. A cylindrical bar of steel, 10 millimeters in diameter, is to be deformed elastically by application of a force along the bar axis. Determine the force that will produce an elastic reduction of 0.003 millimeters in diameter. And we're given the elastic modulus as 207 gigapascals and the Poisson's ratio of 0.3. So what the question is asking us to do is work out the force that will produce a reduction in diameter of 0.003 millimeters for the steel sample. So we're given a radial change, but we need the length change for the equation for tensile stress. So first we work out the strain in the z direction by using Poisson's ratio, and we solve for the strain in the z direction. Which is 0.001. Then we can work out the tensile stress by taking the elastic modulus of the material and multiplying it by the engineering strain, which we've just got from the Poisson's ratio. And we can use the equation for engineering stress, F over A, to calculate this force, which comes out as 16,260 newtons. Now that Young's modulus, or the elastic modulus of a material, is a measure of its stiffness, if you like. It's the resistance that it has to an applied stress. If you have a higher Young's modulus, it means that your material is stiffer and it's more resistant to change. And we tend to group them according to material class. So you'll see that things like, if you look at the difference between a metal and a polymer, look at the difference in Young's modulus. So metals tend to have Young's moduli of anything between 40 to 400 gigapascals. And look at the difference you see between metals and polymers. Polymers have Young's moduli of around 0.2 to 4 or 6 gigapascals. That tells you something about the nature of the bonding in those materials. Look at the differences in metals versus ceramics. Okay, so we've performed our simple tension test, and we'll now focus on plastic deformation. So we move away from this linear region where there is a linear relationship between engineering stress and engineering strain. And there's a couple of parameters that we should be aware of here. First is this parameter we call the yield strength. So this is the stress at which noticeable plastic deformation has occurred. It's called the yield strength. And we usually measure it by offsetting the value in strain. So the minute you start to see a deviation in linearity when you plot stress versus strain, the moment you realize that you've got noticeable plastic deformation, we call that the yield strength of a material, i.e. we've gone past the point by where deformation is reversible. And you can compare the yield strengths for various materials there. You'll notice that metals have a huge range of yield strengths, metals and their alloys. The tensile strength of a material is where you have, is the point of maximum stress on the engineering stress strain curve. So the curve that I show you there is a classic example of a stress strain curve for a metal. You've got that linear region, then you exceed the yield strength of the material and you enter the plastic deformation region. And as the material starts to weaken, the graph undergoes a curve essentially. So the maximum stress on the engineering stress strain curve is known as the tensile strength. And again, you can compare the values for different materials there. What about the ductility of a sample? How do we measure ductility? This is essentially the plastic tensile strain at failure of a material, and we can think about it in a couple of different ways. Basically, we're measuring the percentage elongation of a material up to its failure point. So we can either measure it as a function of percentage elongation, or if we're thinking about a tensile load, we can measure it as a reduction in area, in cross-sectional area, if you like, because remember that the sample is getting smaller. The toughness of a material is essentially the energy that's required to break a unit volume of a material. And we can approximate that by the area under the stress strain curve. The hardness of a material is defined as a measure of a material's resistance to plastic deformation. And there are lots of different hardness tests that you can measure, or that you can use to measure the hardness of a material. Most of them revolve around the idea of measuring the resistance to permanently indenting the surface. If you've got a large hardness, it means that you've got some kind of resistance to plastic deformation or cracking. And it also means you've got better wear properties for your material. There are lots of different ways to measure hardness, and you have to think about the material that you're trying to measure in order to pick your method. One consideration is it depends on the value that you think the hardness of your material has. You can see that basically what it involves is taking some kind of indentation head and forcing it into the material and trying to measure whether or not how much that material has resisted indentation. There are lots of different types of indentation heads, some are round, some are pointed, and they're all composed of different materials. Here are two examples, the Rockwell hardness measurement and the Brinell hardness measurement. One of the major advantages of using the Brinell hardness technique is that there's a kind of loose conversion that can be done between the Brinell hardness value and the tensile strength of the material. That's very useful if you haven't got a way of measuring the tensile strength of the material. You can just take its hardness and calculate it based on its Brinell hardness. The thing is that hardness scales are a bit relative because they're all composed of the heads that indent the material are all composed of different materials themselves, and there's a big variation in hardness of different materials. So it's very difficult to compare different hardness scales. It's very difficult, for example, to compare the Brinell hardness with something called the Mohs hardness. The best way, therefore, is to forget about hardness measurements and stick to tensile stress measurements. There's a quick example question here. It asks you to estimate the Brinell and Rockwell hardness for a naval brass specimen in the following stress strain plot. And if you look back on the previous slides, you'll see that it's possible to interconvert between tensile strength and the Brinell hardness number. When you do that, you get a value of 130 for the Brinell hardness. Then you have to look at the comparison of the Brinell hardness scale with the Rockwell hardness scale and estimate the value for the Rockwell hardness scale. So you can see the measurements here are a lot less precise than if you were just measuring tensile strength of a material with the proper setup and the mathematics that involves. Okay, so stress and strain then are size-dependent measures of load and displacement. The elastic region of a material is reversible, and there is a linear relationship between stress and strain. The plastic region of a material under deformation is permanent, and it occurs when we reach the yield strength of a material. Toughness can be thought of as the energy needed to break a unit volume of a material. Ductility is the plastic strain at the failure point for a material, and hardness is a difficult one to measure because it's not really a very well-defined material property.